Hello everyone, in this session I will share with you some design issue of the FIR filter design. FIR filter design starts with the design of the low pass filter. The design of other types of filter is then based on the appropriate spectral transformations. This means that if you want to design for the band pass or high pass filter, so it based on the appropriate spectral information to transform it to the high pass or band pass. But we must start from the low pass filter first. This graph shows the magnitude of a filter, and this graph shows that this is the ripple and for the pass band, and this is the ripple for the stop band. For the highest number of ripple is called 1 plus delta p. For the lowest value of the pass band is called 1 minus delta p. And this is the transition from the pass band to a stop band. Okay, this is transition period. Fp refers to the frequency of pass band. Fs refers to frequency of the stop band. So this is the stop band. This figure is displayed in the 20 log HF, also the magnitude. Okay, and this graph shows that the attenuation at the pass band and attenuation of the stop band. Pass band ripple refers to the maximum deviation from unit gain, whereas stop band ripple delta S is refer to the maximum deviation from the zero gain. So the gain specification of the FIR filter is based on the pass band ripple and the stop band ripple, which is referred to this, the pass band ripple and the stop band ripple. Since the decibel gain is normalized with respect to the pass band and the stop band attenuation, that is the AP and AS, and this ripple can be described in this equation. Okay, AP equal to negative 20 log A minus delta P, A plus delta P. For the stop band attenuation, you have the negative 20 logs delta S 1 divided by 1 plus delta P. Okay, AP and AS is referred to this one. This one is for the 20 log. And then to convert the attenuation in dB to a value for the ripple parameter, we can use delta P like this. Okay, this is the formula for delta P and for the delta S. Window-based design calls for the normalization of the design frequency by sampling the frequency, and then developing the low-pass filter by windowing the impulse response, and also conversion to the required filter types using spectral transformation. The choice of the cutoff frequency also affected by the window length N. The smallest length N, that means that meet the specification, depends on the choice of the window. Choice of the window in turn depends on the stop band, and this stop band is referred to the stop band attenuation specification. What is the characteristics of the window spectrum? Okay, for the window spectrum, the ideal impulse response, that is the Hn, is multiplied with the window Wn. This is the window and this is the ideal filter. And then the spectrum of the window impulse response is the Hn multiplied with the Wn, and we have the Hwn. This one is the Hwn. So we call it as a window impulse response. The other characteristic of the window spectrum include the ideal spectrum has a jump discontinuity at F equal to Fc. And then the window spectrum show an overshoot and ripples and the finite transition width but no abrupt jump. Its magnitude at F equal to Fc equal to 0.5, which is equal to 6 dB. And then it excludes the window whose amplitude spectrum is entirely positive and result in complete elimination of overshoot and the eclipse effect. And the last one is the number vary in literature, and the value in table of characteristics in the window spectrum were found here by using the ideal impulse response. Okay, Hn with the Wc equal to 0.5, window by 51 points of window. So the magnitude spectrum are normalized with respect to the peak magnitude, and both the Windows function and the impulse response are symmetric sequence. The spectrum of the window filter is also endowed with a symmetry. And this is the characteristic of the window spectrum for different types of windows, such as the boxcar, cosine, Riemann, Henning, and Blackman. And this one is each of them has its own peak ripple, passband attenuation, peak side lobe attenuation, and the transition width. So this is the number. So this is the characteristic of the window spectrum. After we know the characteristic of the window spectrum, but how to select the window and design the parameter? How to select? Okay, here is the guideline. The choice of the window is based on the design of a stop bank specification, the AS. And then the peak side lobe attenuation, AWS, of the window spectrum should match the specific stop bank attenuation. And also the peak passband attenuation, AWP, of the window spectrum should not exceed the specific passband attenuation, AP. And then the window spectrum is the convolution of the spectra of the impulse response and the window function. And this spectrum changes as we change the filter length. And then the three most commonly used windows are the von Hahn, Hamming, and the Kaizen windows. Next is how to choose the filter length. The transition width with the window spectrum decreases with the length n. There is no accurate way to establish the minimum filter length and that meets the design specifications. However, empirical estimates are based on matching the given transition width specification Ft to the transition width of the window spectrum. So Ft is equal to Fs minus Fp, okay, or equal to C over N. Fp and Fs are the digital passband frequency and digital stopband frequency respectively. Then the window length depends on the choice of the window, which means the choice of C. Okay, the choice of C. So the closer the match between the stopband, the AS, the stopband attenuation, and also the stopband attenuation AWS of the window spectrum, the smaller is the window length N. Okay, so in any case, in this relation typically overestimate the smallest filter length, and we can often decrease this length and still meet the desired specification. This is how we choose the filter length. Let's talk about the Kaizen window. Okay, Kaizen window, first of all, we compute the peak passband ripple first, and then the peak stopband ripple, and choose the smallest of this ripple parameter. Okay, minimum delta P and delta S. Then the ripple parameter is used to recompute the actual stopband attenuation, okay, AS. And this is the filter length can be estimated using this formula for the AS 0 more than 21 dB, and this is for the less than 21 dB. And then the Kaizen window parameter beta also can be estimated from the actual stopband attenuation as this one. Okay, this one is for the AS 0 more than 50 dB, and this is in between 21 to 50, and this is less than 21 dB will be get 0. In order to choose the suitable cutoff frequency, a common choice of the cutoff frequency always can be expressed like 0.5 Fp plus Fs. And then the actual frequency that meets the specification for the smallest length is often less than this value. The actual one often less than the estimate one. So the cutoff frequency is affected by the filter length. Okay, a design that ensures the minimum length N is based on the starting with the above value of Fc and reduce the length until we get the mean specification. Okay, means that at the passband at edge. If you want to design the other filters such as the band pass or high pass filter, then first of all you must start with the low pass filter first, then followed by using the suitable spectral transformation to convert it to the required filter type. And these spectral transformation are developed from the shifting and modulation properties of the discrete time Fourier transform. And then it's the same thing again, starting with the ideal low pass filter with the unique passband gain and the cutoff frequency, okay, with the suitable impulse response. So the window impulse response of the low pass filter is the 2fc sin 2nfc multiplied with the wn, which is in this range. Okay. This is how the transformation from the low pass filter to a high pass filter. Okay. So FC is using this expression, and this is the expression for the high pass impulse response. Okay, but this is valid only for filter length is odd value or odd number, and its cutoff frequency is equal to the cutoff frequency of the low pass filter. Whereas this spectral transformation is suitable for any length value. But just now the first transformation is only valid for the odd number only, odd value only. Next, we would like to talk about from the low pass to band pass or band stop. So both the low pass to band pass transformation and the low pass to band stop transformation is symmetric about the center frequency F0. If the band edge are F1, F2, F3, and F4 is in increasing order, the arithmetic symmetric means that F1 plus F2 equal to F2 plus F3 equal to 2F0. This means that this implies is an equal transition width. So if the transition width are not equal, a band edge must be relocated to make sure both transition widths equal to the smaller width. So if the band pass is like this, no arithmetic symmetric, so we need to relocate, okay, the F4, this value. So we move to here so that it is in a symmetric, arithmetic symmetric. And this is the transformation for the band pass, and this is the transformation for the band stop. This table summarizes the impulse response of the window filter from the low pass to high pass. Okay, this is the frequency formula or expression we use, and this is the transformation expression we use. And then next one is the low pass to band pass and low pass to band stop. So this is the frequency used, and this is the transformation, okay, with the range like this. Lastly, I would like to share the recipe for the window-based FIR filter design. First of all, normalize the analog design frequency by the sampling frequency S. Then obtain the band edge FP and Fs of the low pass prototype. Then number 3, choose the low pass prototype cutoff frequency as the 0.5 Fp plus Fs. Number 4, choose a window from the table in slide 31 that satisfies AWS. AWS is referred to the peak side loop attenuation more than the stop band attenuation, and AWP, that is the passband attenuation, less than or equal to the passband attenuation. Then compute the window length n from the Ft equal to Fs minus Fp or equal to the window spectrum width, which is equal to C over n. This is the transition width Ft. Then the C value is in the slide 31. Next is the compute the prototype impulse response. This is equal to the symmetric truncation, in which the Hn is equal to 2fc sin 2nfc in this range. Okay, this means it's minus 0.5 n minus 1 less than or equal to n and less than equal to 0.5 n minus 1. That's why you have the modulus here. And then next is to find the Wn using the equation from slide 9, depends on the window type. Calculate for each n and show the Wn in numeric. Then find the HWN, which is equal to HN multiplied with the WN. This is the point-wise product. And then for the low pass to low pass, the HW no need to convert. But if from the low pass to high pass, band stop and band pass, the HWN need to change to the H filter N. So this is how to transfer to the HWN to the desired filter. Let's say you have a low pass to high pass. This one you can refer to slide 39. There are two ways. First is this one, which is varied for n is odd number only. If you have n as the even number, you can use this value. But both methods will give the same answer. Next is the low pass to band pass. So if the transition widths are not equal, a band edge must be relocated to make both transition widths equal to the smaller width. And this one you have the FC and the spectral transition. And this one is the low pass to band stop. You can use this expression for the transition to the band stop. And next is, if necessary, convert to a caudal, and then finally change to a Z transform. So that's all for the recipe of the window-based FIR filter design. Hope you can understand. And next session, I will share with you an example of the FIR filter design.